The first type of problem is when we're given the solubility and we're asked to find the KSP. So we're given here that the solubility of copper hydroxide is 1.72 grams per 100 milliliters at 25 degrees Celsius, and it asks us to determine the KSP. Now, in order to determine the KSP, we need to be working with the molar solubility. So what we're going to do here is first change the solubility that's given to us in grams per 100 milliliters to a molar solubility. So the molar mass for the copper hydroxide is equal to 97.57 grams per mole. And what we have here is a solution where 1.72 times 10 to the negative 6 grams of this is dissolved in 100 milliliters. So we can determine the moles, okay, by doing moles is equal to mass divided by molar mass. So the moles that we have here is 1.76 times 10 to the negative 8. To find the molar solubility, we want the concentration that can dissolve in moles per liter. So we've got 1.76 times 10 to the negative 8 moles dissolved in 100 milliliters, which is 0.1 liters. So the molar solubility of the copper hydroxide is 1.76 times 10 to the negative 7 moles per liter. We're going to use the variable S to describe solubility. Now, in order to determine the equilibrium constant for this reaction, what we need to do is examine the equilibrium that we're studying here. We're studying a solubility equilibrium, so it is the equilibrium of that solid dissolved in water, and we break it up into its ions. Now, when we are thinking about something dissolving, we're actually thinking about this substance dissolving in water. And it's the solubility that defines the amount of this that can dissolve. Okay, this is the amount of copper hydroxide that can dissolve in water. So essentially, we start with none of this dissolved. And what we do when we study solubility equilibrium, instead of using X, we use S to describe the changes. So this is increasing by S. And this is increasing by 2S. Okay, because if we think about this, I'm going to put it in brackets as S because it's a solid, so we're not actually going to involve it in our calculations. But what we're doing here is thinking about this substance breaking up into its ions. And for every one of these, we put into the equilibrium 1 copper ion and 2 hydroxide ions. Okay, so we're applying the ratio here. So at equilibrium, this is S and this is 2S. So the amount of this that's able to dissolve, because this essentially goes down to 0 at equilibrium because all of it dissolves, it will allow us to know what S is and therefore know what the concentration of the copper ions and the hydroxide ions will be in this saturated solution. So to find the KSP, we're taking the concentration of the copper ions that we have and the concentration of the hydroxide ions that we have squared. So we know what the concentration of the copper ions is 1.76 times 10 to the negative 7. And the concentration of the hydroxide here is 2 times S, so it's 1.53 times 10 to the negative 7. Okay, and we are squaring that because that's what we need to do based on the equilibrium expression. So what we have here is 2.19 times 10 to the negative 20. It's a very small KSP value, but it's what we would expect if you look at the solubility. This is a tiny amount of copper hydroxide that can dissolve into this solution. Okay, so it makes sense that we have a very small KSP value. If we want to go the other direction, so if we're given the KSP and we want to know the solubility, okay, we need to look up in our table what the KSP value is. So for this one, we're dealing with barium sulfate, and we look up the KSP value is 1 times 10 to the negative 10. So barium sulfate, when we're studying it, its equilibrium is barium 2 plus SO4 2 minus. Okay, this is another case in the year where knowing your polyatomic ions is very useful. And when we look at this equilibrium, when we're dealing with solubility, we're starting with none of these dissolved, and then the maximum solubility of barium sulfate is the amount that's actually going to dissolve. So each of these, because they're in a 1-to-1 ratio, will have a concentration of S at equilibrium. So when we sub into the equilibrium law, which is barium hydroxide times sulfate, we're going to have S squared is equal to 1.1 times 10 to the negative 10. So S in this case is equal to 1.1 times 10 to the negative 5, and that's in mole per liter. Okay, so when you solve for the traditional X from your ice charts, what you're actually determining is the solubility in moles per liter of the particular substance. For zinc hydroxide, it's a little bit different because we have a ratio other than 1-to-1. When we look at zinc hydroxide, we get Zn2 plus 2 hydroxide. And for these, they're all the same. So if you want to skip ahead to just the ice chart, the E row, okay, this is going to be S and this is going to be 2S. Okay, your ions always start at 0 and always increase in the ratio that is reflected in the equation. We have S and 2S. The key here is that we've got this 2S and we also have a KSP expression that considers that 2S. So we've got zinc times hydroxide squared. So we're going to have S times 2S all squared, which is 4S cubed. When we look up the KSP value for this, we find that it is 7.7 times 10 to the negative 17. When we solve for S here, we get 2.68 times 10 to the negative 6 moles per liter. So the solubility here is in moles per liter. So this is the molar solubility, but we're asked for solubility. And what you need to assume is that if you're just asked for solubility, that it's asking you for the grams per liter. So if we want to find the solubility in grams per liter, we need to take the S and multiply by the molar mass of the zinc hydroxide, which in this case is 99.41. And we find that we get 2.66 times 10 to the negative 4 grams per liter. Okay, so example 1 and 2 are going from KSP to solubility and solubility to KSP.